skipped over, we did this first problem, then I didn't see that it was lingering down at the bottom. So let's do another integration by parts on this problem, and then we'll carry on. So the cool thing about integration by parts is that it allows us to integrate a product, and it also allows us to integrate a lot of other things that we saw at the end of class last time. We could integrate the natural log function, we could integrate the inverse trig functions. It's kind of cool that you can use this technique to get some antiderivatives for some of the more obscure functions. So let's take a look at this. The first thing we do is identify u and dv. So we have to pick a u and we have to pick a dv. And we know that the dx has to go with the dv. So this is kind of where we start every time we're going to do integration by parts. So we know that much right there. That's kind of the outline of what we're going to do. And how many functions are you seeing in there? Yeah, there's two main functions, right? There's the x squared and there's the natural log of x. And so we can pick whichever one we want. I'm just going to rearrange this thing right here. I want that down there. So we are just going to pick, and we have basically two choices. We basically have two choices. We could put the x squared with the u, or the x squared with the dv. If we put the x squared with the u, then we would put the natural log with the other one. Now notice, though, that if we were to put the natural log right there, to get to v from dv, we'd have to integrate, and we don't know the antiderivative of natural log x off the top of our head. Maybe some of you picked up on it last class, x ln x minus x, but that's kind of a complicated antiderivative, so usually we won't put, even if we know the antiderivative for log, usually we won't put it there. So right off the bat then I'm thinking, oh, well, natural log is kind of an oddball function, so let's put it over there, and let's put the x squared there. And this goes a little bit counter to one of the suggestions I gave you last time. The two main tips are, if you put powers of x here, then the power decreases, which is nice for that secondary integral that we're going to get. But in this case, what we're going to notice is that the derivative of natural log of x is going to take away an x because its derivative is 1 over x. So there's going to be an x in the bottom.
Is that why last time you said sometimes you have to do ultraviolet voodoo 2 or 3 times because you might end up with a situation like this where, like, say you want to take the integral of ln of x, but you don't know what it is, you have to do ultraviolet voodoo to find that out and then plug it in.
Right, exactly. Yeah, so if we wanted to put the ln x over here, we'd have to go do integration by parts just to get this one piece, which is more work than we want. And sometimes with these powers, you can do integration by parts many times, which we'll see soon. So let's see how this works out. But notice that when we take this derivative, we get a division by x. So even though over here we're increasing the power, which feels counterintuitive, to make it simpler, seems counterintuitive. But what we're going to notice when we do that is that our uv is going to be 1/3 x cubed ln of x. So that's the main diagonal. uv minus integral v to u. Here's our voodoo, bottom row. And notice that when we do this, we end up with 1/3 x squared dx. And that's our crossroads right there. Here's where we say, is this integral easier than this integral? Well, yeah, the log is gone. And so that worked out really well, putting the natural log here, because it turned into division by x, which then simplified really nicely. So if you get to this integral and it's not easier than that, that's when you go back and switch your u and your dv. You try the other way and see if it works. And this, of course, we can integrate this really easily. So we have the 1/3 x cubed ln x out in front. And then we integrate this, we get x cubed over 3. And the 3's combine. And there is our antiderivative. Or more correctly, the family of antiderivatives. There's an infinite number of antiderivatives. Sometimes they call it the general antiderivative or the family of antiderivatives. Usually we just shortcut it to just say the antiderivative. Any questions on any of the steps? All right, so let's see. So let's go here. So we did a couple of examples where we used integration by parts, ultraviolet voodoo, to integrate these functions that aren't products. We don't see a product there, but it worked really well to get to antiderivatives for any inverse trig function it works nice for, or for the log function it works great for. So here's where we might need to use integration by parts repeatedly. So let's take a look at that, how we might have to use it more than once. So again, we're going to start with u and dv. So we always start right here. You know, we build this little table. We know that we're going to have those 4 pieces. So the top row, and some people do it a little differently. I always do the top row is going to match exactly what's in the integrand. So the dv, the dx has to go here. And we need to now split. I'm seeing this as 2 functions. Natural log quantity squared and x squared. And once again, the natural log squared of x, also you could call it natural log of x quantity squared, same thing. That's not easily integrable. That's going to be a very difficult integral. So most likely what we're going to want to do is that and that. All right? Natural log all by itself is hard to integrate. If it's natural log squared, that's going to be an integration by parts all by itself. So let's do this. So with the antiderivative over here, we're going to get an x cubed over 3. And once again, let me just point out that we're choosing the constant of integration to be 0. And you could pick whatever constant of integration you want. You could pick pi if you want, but who would do that? Let's pick 0. Any antiderivative constant you want to pick will work. We always pick 0 because it's simplest. So then we come over here to take the derivative, and I need a little more space most likely. So du, we're going to have to use the chain rule. So remember that this is like y equals natural log of x quantity squared. So first we pull the power. So 2 natural log of x to the 1. So pulling the power, 2 natural log of x to the 1. And then we have to differentiate the base. So the power rule, that's the outside. 2 comes down, subtract 1, leave the base alone. But then we have to differentiate the base. And what is the derivative of the base? It's going to be 1 over x, right? The derivative of the log function is 1 over x. And then we have to have the dx in there. So there's our recipe. Those are all the ingredients for our ultraviolet voodoo. Those are the ingredients. So the first step then is the main diagonal. So that main diagonal, we're going to do uv, so that times that, main diagonal, uv. So we will have 1/3 times x cubed times natural log squared of x. That's u times v, minus the integral of the bottom row, the voodoo. Voodoo is the bottom row. So we multiply this together. The constants, I see a 2 in the top, a 3 in the bottom, so there's going to be a 2/3 as the constant. You can pull it right to the front of the integral if you want. 2/3. And now the x is going to go into the x cubed, giving us an x squared. And then we have a natural log of x. and a dx. And here's the crossroads. Here's where we say, is this integral easier than the original? And if it is, then we keep on going. Is that integral easier? Yeah. The power on natural log dropped. Right? The power on natural log went from 2 to 1, and the x squared stayed the same. So that's good. This is good. So we're going to do integration by parts again, a second time. And we have to be careful here. Because there is this leading negative sign, you just have to be careful. Right? Because you're going to end up with big brackets, and that minus will have to be distributed. Because we're going to have to do a whole nother uv minus integral of v du for this with a leading minus. Now, if you want to be clever, you could do this. You could say, hey, let's make this a plus, and let's put the minus right in here. Then it's part of the next recipe. So there's a couple of ways you could go. Some people might say, hey, let's factor out the 2/3, which is fine. You can factor that out to the front, but then you're going to have monster brackets and distribute that negative 2/3 across. So the most efficient way is to actually just leave, if you have to use integration by parts again, push everything inside the integral and have a plus out here. That's going to be the safest way not to blow a constant or a sign. If you just move it inside and make that positive, now we're going to do a second iteration of integration by parts. And we want to stick with the same pattern that we used in the first integration by parts. If you don't, you'll just undo what you already did. So we want to stick with the same pattern. And by that, I mean if you pick the log for u in the first one, pick the log for u in the second one. So we're going to come over here and we're going to say, oh, okay, so we have a log there. And I'm thinking of these two functions here. And the negative 2/3 could go with the x squared or it could go with the natural log. That does not matter. But you need the x's with the dv again, and you need the log with the u again. So let's see what we get. Okay, so I'm going to let u be negative 2/3, I'm going to let u be natural log of x. And I'm going to let dv be negative 2/3 x squared dx. And then on the left, in the left column, we're going to take the derivative. So du will be 1 over x dx. Integrate over here, and we're going to get minus 2/9 x cubed. And now we're ready to do our second integration by parts. So, because we have a +1 out in front, we don't have to worry about distributing constants, distributing minus signs. It's all good to go. So next line, we're going to have the 1/3 x cubed natural log squared of x plus u times v. Oh, uv is negative. So this will be a negative. So it's going to be negative 2/9. So the signs just work out beautifully if you let the sign, if it was negative, if you just push it inside, they're all going to come out fine. You don't have to do any stressful distribution. So there's uv. uv minus the integral of v du. So now we look down at v du. Oh, v du is negative. So that's going to mean this will be plus 2/9. 1 over x times x cubed is x squared dx. And then we ask that question again. We're at the crossroads. Is that integral easier than the original? Yeah. Now the log is gone. And we can integrate that. So our next step, these two things just carry down. And this is going to be x cubed over 3, so we're going to get 2 27ths plus c. So there is the antiderivative. All right, any questions on that? Anything cause you anxiety?
Why would the second then not go in the first, or the second iteration not go in the first integration? Let's just not work about that.
Say that again. Why would I don't have a paste?
Oh wait, no, not. I think I just answered my question.
Where's my paste? How do I right click? Say that again, Ari. Or did you figure that out?
I got it.
Don't have my. I need a paste up there. Do I not have a paste up there? It's the shapes. Gotta get a paste up there. Yeah.
So when we do this use substitution, you said that we can make the constant any number we want. We just do 0 because it's easier. Would there be a situation where making it not 0 would help out?
No.
Okay.
No. Making it 0 is always going to be
Would
best.
always be best.
Yeah, always be it. So whenever you do these the integration within your integration by parts table here, always choose 0. Yeah, Carter?
When would it be even necessary? Would it ever be necessary to do it?
To not do 0?
Yeah.
No.
Oh, so it's just a feature that literally has no purpose.
Well, the feature is that you can pick whatever constant you want. Picking 0 is just the easiest way to go. If you pick this constant to be something else like +5, in the end you're going to get a +5 and a -5 and they're going to cancel and it will just go away. So picking 0 is just the most efficient way. Yeah.
That ln squared x, is that the same thing as saying ln x?
Quantity squared.
Okay.
So this is the first book that I've seen this shorthand notation. So they're using that shorthand notation that we use on trig functions for this, which this is the first book I've ever seen it in. So yeah, if you don't like it, write ln x quantity squared like that. Yeah, but that's what it means. And the notation, yeah, it makes perfect sense if you're used to the trig notation. But it looks weird. First time I saw it when we opened this book, I was like, oh, that's interesting. Never seen it before. All right, so, all right.
Are you going to be heavy on simplifying in this chapter?
Do you see, where's there a spot there that you feel like you would rather not simplify? On this test, I will be more strict on simplifying, yes. Maybe that answers your question. Yeah, you want to always simplify. All right, you all try this one. So this is going to be an integration by parts that you have to do 2 times. So see if you can figure it out. Costa Rica for spring break a couple of years ago. I was drinking all sorts of weird stuff.
He's good.
So hopefully as you're setting up your integration by parts, you're sort of thinking to yourself, the x squared, if you differentiate it, that power is going down. With the exponential, regardless of whether you put it with the u or the dv, it's going to just sort of stay the same. Like the derivative in the integral of e to the x is e to the x. So it's going to be, the only way this will work is if you put the x's with the u. X is with the u. I'll start catching up to you. That's what you should have for your first integration by parts. So here's one of those examples where the more you do it, the more you realize this little clever trick is really helpful. So if you make that a plus and you make that a minus in there, then you don't have to worry about distributing a minus sign. When you do that integration by parts that second time, if you had a minus sign out in front, then it would have to be distributed across this whole quantity. Similarly with that 1/2, it's safest just to leave it inside the integral and let it sort of come out in the wash as part of the next u in the dv. So that's our second one. And once again, do the same thing. If you switch and you put the exponential with the u and the x with the dv, you're just going to undo what you just did in the first integration by parts. You want to be consistent. If you put x's with u originally, do it again. So we're going to put the minus 1/2 x there, and we're going to put the exponential over there. Any questions on that? Does that make sense conceptually? So then our du here is going to be minus 1/2 times dx. And our v here is going to be e to the 4x divided by 4. So I'm grouping this. This is going to be my u. Not sure what happened. That's going to be the u, and that's going to be the dv is going to be all that. All right, so let's finish it off down here. So we've got 1/4 x squared e to the 4x plus u times v. Oh, uv is negative. So this will actually be negative 1/8 x e to the 4x. So that's the main diagonal. Right there, multiply together. So uv minus the integral of v du. V du is voodoo, that's the bottom row. Oh, I see that voodoo is negative, right? Negative right there. So that negative comes out, it's going to make that positive. And we're going to have 1/8 e to the 4x.
When would you multiply by 1/2? Right, you get to multiply the bottom row.
So the bottom row is multiplied
Oh,
together
okay.
into, you see it?
Yeah.
And then we're at crossroads. Looks easier, so we're on the right track. And it's so much easier that we don't have to do integration by parts again. So when we do this, we're going to get integral of an exponential is itself. Reverse chain rule says take the derivative of the exponent, divide by it. So 1/8 divided by 4 is 1/32. And then we have our constant of integration. So we've got all that. And we'll bring this down. Got to go get the paste command. Copy. Thought I should be able to just hold that down and have that menu pop up. Does not want to pop up.
When it comes to our expectations for the exam, are we gonna have to do like 3 or 4 u substitute?
No, I will not have you do 3 or 4 integration by parts.
So max would be
2 is, yeah, 2 is enough.
When I'm talking about simplification, I mean like, would you want us to, for the first part before the integral, match denominators or like factors?
No,
Okay.
because we're going to have the plus c, so it's actually best just to leave all the terms individual. Because if you're going to factor, you can't factor out of the plus c anyway. So usually we're only going to factor if you can factor out of everything. So yes, you could factor out an e to the 4x there, but there's no benefit in that, so that wouldn't be considered simplifying. It's only going to be considered simplifying if you could pull it out of everything. And there's no need to get a common denominator. These have different powers of x, so we can't combine them. All right, so yeah, that would be simplified there. All right, so integration by parts repeated. Let's go to the next slide. So here we're going to do some integration by parts where we have a definite integral.
Okay, if we're doing repeated integration by parts, would you dock us points if we did use brackets? Like
No,
brackets?
no, absolutely. Yeah, if you use your brackets correctly and you distribute correctly, that's totally fine. Yeah, because it does take a little bit of practice before you start realizing, oh gosh, it's easier if there's a plus in front of the integral. It takes time. And I didn't even start doing that until I'd been teaching this for a long time and realized that everyone was screwing up their signs. Because you'd end up with like a minus and a bracket, and then inside there'd be another minus, and then there'd be another minus inside the next integral. And I just realized at some point that, oh, it's just easier if you keep a plus out in front. And so it might not be natural right away to sort of pull it, because you usually are thinking about taking things out of the integral. Like pushing something into the integral is a little counterintuitive. But if you do a few of them where you leave the minus out and you start seeing all the minuses and how you have to count, oh, there's 3 of them. And so that will be a minus in the long run. Ideally, giving you that idea ahead of time, you can start to use it and it'll just make your life a lot easier in the long run. But if you use the brackets with the minus out in front, that's totally fine. Totally fine also. Okay, so here we have, once again, we see the integral of a log function. And we don't know most of us don't know the antiderivative off the top of our head. So we're going to use integration by parts here. So we're going to have a u and a dv. And once again, it's obvious that we want to put the log with the u. Because if we put it over with the dv, then you're asking the same question. You're saying, hey, what's the integral of natural log of 2x? And we don't know. So that's why we're going to put it with the du. And can someone tell me what the derivative of natural log 2x is? Everyone agree?
It'd be 2 over x.
So let's think about it. So the rule for a log, it's 1 over the inside, so 1 over 2x, multiplied by the derivative of the inside. So you get a 1 over 2x, but then you multiply by 2, so then the 2's cancel. Everyone following that?
Yeah.
So if you take natural log of 2x, the derivative is 1 over the inside, but then you differentiate by the derivative of the inside, you multiply by the derivative of the inside, so you get 1 over x. All right, so let's go with our voodoo here. So uv, that's going to be x ln 2x. And now we're going to put the evaluation stuff here, 1 to e. So the uv has to be evaluated on the interval 1 to e. uv minus the integral from 1 to e. Voodoo, bottom row. Ooh, x divided by x is 1. So we end up with just a dx. Yeah, what does this integral evaluate to? Forget about the minus and everything in front, just that. That's going to
Minus
evaluate
1.
e minus 1. If you integrate a differential, you get the length of the interval, which is the upper limit minus the lower limit. So it will be e minus 1.
So to keep that in exact terms, we just write e minus 1.
Right.
Okay.
So let's evaluate over here. We're going to have e times natural log of 2e minus 1 times natural log of 2 minus the quantity e minus 1. All right, so a couple of things we can do to simplify here. Let's think about this. So we have an e here. How about natural log of a product? Well, what can we do with natural log of a product? Make that what? So I'm just taking this natural log of 2e. How do we rewrite that?
Natural log of 2 plus natural log of 2?
You could pull that up, but we don't want to pull that up. We want to simplify it, so we want to break it apart into what, Austin?
Natural log of 2 plus natural log of e.
Right? So the product rule for a log says that the log of a product is a sum of logs. It's essentially the law of exponents. So this is going to be natural log of 2 plus natural log of e. And then we have minus natural log of 2 minus e minus a minus is plus 1. And what is natural log of e? 1. So this is going to end up being e natural log of 2 plus e minus natural log of 2 minus e plus 1. So the e's are going to cancel, and we're going to end up with e ln of 2 minus ln of 2 plus 1. And we're not going to do any factoring here because there's nothing common to all 3 terms. Factoring out the natural log of 2 from the first 2 terms, that's not going to benefit us. All right, any step there that you want to ask about? Everyone okay? Now, all right, let's go for this one. So first, let's highlight the functions. I'm seeing 2 functions. I see this arctangent function, and I see the y out in front. So there are two functions. So we have a product. Integration by parts is a natural choice if you have a product. Is it clear that you can't just use substitution here? Like if you were to let u be arctangent, the derivative of arctangent is not in front. You could simplify it a little bit by doing u equals y squared. Actually, you could do substitution that way. You're going to end up having to do integration by parts anyway. But if you did want to do substitution here to get it started, you would let u be y squared, not inverse tangent of y squared. And that would not save you much time anyway. So here we go. Ooh, that's not what I wanted to do. I wanted to do that. That's still not going to take that. So let's let u equal the inverse tangent function because we don't know the antiderivative for that. You know the derivative, not the antiderivative. Correct?
Correct.
Right? You know the derivative is the 1 over 1 plus x squared form. So we're going to break apart the integrand. Top row, u dv. Everything should be used up. V is integral, so we're going to get y squared over 2. Here is the derivative. So du equals derivative of arctan. Think about it before I write it down. So we're going to have 1 over, say that again, 1 over what?
Is it 1 over x plus 2 squared? No.
1 over 1 plus x squared. So 1 over what? Y to the 4th? It's normally 1 over 1 plus the inside squared. The inside is now y squared, so when we square the inside, we get y to the 4th. If there's one more step, multiply it by 2y, the derivative of the inside. So the derivative of the inside is 2y. So derivative of arctan is 1 over 1 plus the inside squared. So squaring the inside gets us to a y to the 4th. Right, that is going to give us uv of half y squared arctan of y squared. So there's uv, ultraviolet. Ultraviolet, now voodoo, so minus the integral of v du, bottom row. Multiplying the bottom row here, do you see that these are going to cancel? There's a 2 in the top and a 2 in the bottom. Everything's multiplying. So those cancel. So we're going to end up with y cubed divided by 1 plus y to the 4th dy. Form. You could do a du sub, but even quicker, log form, right? The derivative of the denominator is 4y cubed, so the numerator is almost the derivative of the denominator.
Multiply the integral by 1/4.
Exactly. So we're going to put a 4 inside. So now it is in log form, but if we put a 4 inside, we have to put a 1/4 on the outside to offset that. Now it's in log form. We're golden. So this is going to equal 1/2 y squared arctangent of y squared minus 1/4 natural log of the denominator. We don't need absolute values because that denominator is always positive. So this is because we are in log form. Oh! I almost said a bad word. So we have one more step to go. Go away, blocks. No C, not yet. So that. So the limits of integration, you can put them here. One thing that we can do is wait. So they certainly need to be on this leading the ultraviolet part, the UV. But we don't have to evaluate right away. We could just wait to the end because the limits of integration are the same. So we can do this. This is totally fine. We just wait and evaluate it at the very end. Limits are the same, so that's fine. Well, let's see. Are we lucky? If we plug in 0, do we get 0? What do y'all think? If we plug in 0, do we get 0?
No.
What is the inverse tangent of 0?
Inverse tangent 0.
Or you might say to yourself, who cares? I know that the inverse tangent is defined everywhere, right? It's got that little sideways S thing. And if you multiply by 0, you get 0 anyway. But inverse tangent of 0 is the angle on the right side of the unit circle with a tangent value of 0, which is 0 radians. So even if that y squared was not there, this is 0. Arctan of 0 is 0. Over here, plug in 0, natural log of 1 is 0, right? Natural log of 1 is 0. Natural log of 1. Do not forget your natural log function. Natural log function looks like that. Natural log of 1 is 0. Okay, so we only have to worry about that upper limit of integration. So let's go with it. So out here, we're going to have 1/2. When that's plugged in for y, we square it. We're going to get a 1/2 multiplied by arctan of 1/2 minus 1/4 natural log 1 plus 1/4. The inverse tangent of 1/2 is not a special angle. The inverse tangent of 1/2 is an angle that's irrational. There's no simplification there. So there's nothing we're going to do. We'll just write it like that. We do not know the angle that has a tangent value of 1/2. We know all sorts of angles that have sine values of 1/2 and cosine values of 1/2, but not tangent of 1/2. The only special angle we really deal with for inverse tangent, or there's 3, the angles that we deal with, arctan of 1 is pi over 4. Arctan of root 3. Arctan of root 3 is? Arctan of root 3 is what?
3?
Okay. So if we look at our unit circle, the 3 angles that we're focusing on are these 3. This point right here is root 3 over 2 comma 1/2. This point here is 1/2 comma root 3 over 2. And inverse tangent is asking for a specific tangent value. Tangent is the same thing as slope when you're talking about points on the unit circle. The slope here is m equals 1, y over x. The slope here, y over x, is root 3, and the slope here is root 3 over 3 if you rationalize the denominator. So the inverse tangent of root 3 is pi over 3. The inverse tangent of root 3 over 3 is pi over 6. And the inverse tangent of 1 is pi over 4. So, all right. And I kind of That reminds me of a really interesting problem. Here's a very cool math equation. The inverse tangent of 1 plus the inverse tangent of 2 plus the inverse tangent of 3 is equal to pi. It's a pretty cool math equation. So this says, this is a sum of 3 angles. This says the angle that has a tangent of 1 plus the angle that has a tangent of 2 plus the angle that has a tangent of 3 all add up to pi. And this can be proved if I take this stack of blocks, right there, stack, these blocks are all 1 by 1 blocks. I can draw 3 lines and prove that to you with 3 lines. Here are the lines. So I'm going to draw 3 lines, and it's going to prove this to you. So I'm going to draw this line. I'm going to draw this line. And I'm going to draw this line. That's the proof. Because this angle right here is inverse tangent of 1. That angle has a tangent of 1, right? Because it's opposite over adjacent. So the angle here, the tangent of this angle is opposite over adjacent, which is 1. So this angle is the inverse tangent of 1. This angle right here is the inverse tangent of 2, because the tangent of that angle is 2. The tangent is opposite, which is 2 diagonals, over adjacent, which is 1 diagonal. This is a right angle here. So that angle is inverse tangent of 2. And this angle is inverse tangent of 3, because its tangent value, opposite over adjacent, is 3. So we've got these 3 angles add up to a flat angle, which is pi radians. Right? 180 degrees is pi radians. Proof with no words. Proof by picture. There's a very cool math book called something like that, Proof by Pictures or something like that. It's kind of a cool book. But that's a nice equation. You're going out and getting a tattoo this weekend. Arctan 1 plus arctan 2 plus arctan 3 is pi.
Is this similar to how like squeeze theorem only works on a graph?
I mean, you can prove this without the graph,
Okay.
but the graph just sort of shows us really clearly, that that's true.
Did you get this from 3 Blue, 1 Brown?
No. I've been doing that problem before that guy was even born. That might not be true. How old is Grant Sanderson? Anyone know? I don't remember I don't know how old he is. But I remember when he used to work for Khan Academy.
He was with Khan Academy?
Yeah, that was his first job out of grad school, I believe. I believe his first job out of grad school was with Khan Academy. Do you guys know Vi Hart?
Heard of it.
Vi Hart's a woman.
Heard.
Victoria, I think is her original name. Vi Hart. Have you seen a Vi Hart video? She makes the coolest math videos. She, 10 years ago, 15 years ago, she was just all over the place because she made the coolest math videos. There's a very fun one called Pi is Wrong.
Oh, yeah. You put that one on there.
Oh, is that one on the list?
Yeah.
There's got to be a Vi Hart one in the
No,
list.
wait a second. Never mind. It was the pi is still wrong.
Pi is still wrong. She did that one too.
Oh yeah, I've had her videos recommended to me.
Yeah, she's fantastic. She spoke at a math conference in Denver about 10 years ago, which was super cool. Okay. And she used to work for Khan Academy too. She was hired as a mathe-musician for Khan Academy. long ago. I don't know if she still works for Khan
Like
Academy.
making music based off patterns?
Yeah, she did some. They just gave her this title, math and musician, for I don't know why.
Okay.
But yeah,
I've
she's
heard the title mathematician.
there's that guy too.
What's the guy's name? Like Arthur Benjamin?
Arthur Benjamin, yes, Arthur Benjamin. That guy's amazing.
Richard Russick.
Okay, so let's go look at this application. So this says we've got one lobe of sine. We've got one bump of sine right there. 0 to pi. We're going to rotate it around the y-axis. So that's going to go around this way. And we want to find the volume of that solid. Volume of that solid. What shape should we use? Disc, washer, or shell? Shell. Using a washer would be the most foolish thing you've ever done. If you tried to make a washer, if you tried to rotate that around, you would have to figure out the length of this, which means you'd have to take the sine curve over here and solve for x, the sine curve over here and solve for x. Inverse sine is a function, so inverse sine is only going to find one of those angles, so then you'd have to add this distance, like this angle distance to it. Not the move. Definitely not the move. So we want to use a washer, so we're going to draw a vertical element at a random x. So that is parallel to the axis of rotation. So parallel to the axis of rotation, this is going to give us a radius right there of our cylinder. There's the radius and there's the height. So the blue line rotates around the y-axis. The green line is the spoke, right? That's reaching from the axis of rotation out to the cylinder, out to the shell. All right. So the area of a shell is 2 pi RH. Circumference 2 pi r times the height gives you the area of a cylinder or a shell. All right. So here we go. So the area of our shell, 2 pi, what is r? Just x. The distance to the axis of rotation, which is the y-axis, is x. Our representative shell is exactly x units away, x radians, from the axis of rotation. And what is the height? Sine of x. So there is our area function. So that area function tells us the area of the cylinder at x radians. If we plugged in our extremes like 0 or pi, we should get 0, and we do. Sine of pi is 0, sine of 0 is 0. All right, so this leads us to volume. Volume will factor out the 2 pi. 2 pi integral x inverse sine of x dx. And we're integrating from 0 to pi. Could we use symmetry here and double it and go 0 to pi over 2? Does everyone see why? These points right here are closer to the axis of rotation. Right? These points are further away from the axis of rotation, so there's going to be more volume out there. Right? Because it's rotating all the way around with a bigger radius. These points are closer, so there's no symmetry here that we could use. Jose, did you have a question?
I was just gonna say you like add them together, but I guess.
Yeah, so they won't be the same in shape.
If we were spinning it about the x-axis, then.
Now,
then
spinning it around the
then we
x-axis,
would use symmetry.
then we could use symmetry.
Then it would be dy.
Yeah. Then it would be dy if we were using a shell.
If you were using a shell.
If we were using a shell.
But you would use disk for that one.
I would use a disk for that one. Okay, so there we have it. Here is a product of functions that we don't know how to integrate. Can't integrate it with u sub. So we're going to use integration by parts. So let's go ahead and set up our little integration by parts formula. So we will have a u, we will have a dv, from the u, we will get a du. From the dv, we will get a v. So when we look at this, you should be seeing two functions. The natural choice here is to put the x with the u. Because the power will go down as you differentiate it. The sine function, regardless of where you put it, it's going to sort of circulate. It's going to be cosine or minus cosine, right? It's going to stay about the same in difficulty. So you don't want to put the x with the dv because then it's going to climb higher, x squared over 2, and this one's going to stay about the same if you put u as a sine of x. So we definitely want to go with the x over here. And now this brings up the thing we talked about earlier. This constant's out in front. Let's leave it out in front this time and just see that we have to use big brackets. It's not going to be a huge deal, but definitely something that on second glance I would be more inclined to actually leave the 2 pi in so I don't have to deal with big brackets. So we've got that. There's our recipe, integration by parts recipe. So we will have 2 pi, but then we have to have big old brackets. And now we have our uv, which is minus x cosine of x from 0 to pi. There's uv, ultraviolet, minus the integral, 0 to pi, of the voodoo. The voodoo minus cosine x is going to force a plus in between. And then we have to have the big old bracket closed off. Totally fine with brackets, but again, it'd actually be a little simpler if I just would have left the 2 pi on the inside and had it part of the UV, part of the ultraviolet voodoo. But no biggie. Any questions on getting to that stage? Sweet. UV minus the integral of v to u minus a minus makes that a plus. Then we do our evaluation. All right, so 2 pi, big old bracket. Plug in the pi first. What's cosine of pi?
1.
Cosine of pi?
0.
Negative 1. Negative 1, so we're going to end up with positive pi minus 0. So when we plug in the 0, we get 0. So plugging in the pi, we get negative pi, negative 1, so that's positive pi, minus 0, so that's that. This part we integrate cosine to get sine. 0 to pi. And how much is that going to contribute? Not much, right? Sine of pi is 0, sine of 0 is 0. So that's going to give us 0. 2 pi pi! 2 pi squared. 2 pi pi.
What if the radius was pi?
Say that again?
What if the radius was pi?
The radius was pi, then
Usually it's like pi r squared, right?
usually? What do you mean by usually? Like when you're randomly collecting pies, you get 2 pi r squared? Yeah.
It's just that answer is just weird.
Yeah, it's weird. Weird is good. Keep math weird. Okay, so that is our volume. That is our volume, 2 pi squared cubic units. 2 pi squared cubic units. All right, let's go ahead and take our 10-minute break. 10-minute break. And enjoy your 10 minutes. Caitlin's ready. So we are now at integration by parts with a twist. When integration by parts repeated isn't enough, we need to just throw in a twist. Just a twist. A little bit of lemon. So here's what we're going to do. When we look at this, we definitely see a product. We see a pair of functions. We see the exponential function. We see the sine function. So we are going to use integration by parts. It's a product. It makes sense to go with integration by parts. But one thing that you sort of notice, hopefully fairly quickly, is that neither one of those functions is going to either differentiate or integrate to a simpler function. The exponential differentiates and integrates basically to itself. The sine function differentiates and integrates to cosine. Right? So neither of them is sort of differentiating down to 0. Like if you had a power of x, it would differentiate down to 0. So this is what we mean by a twist. So you'll see as we start to go here. And with these ones that have a twist, they will be functions that are circular like that as you differentiate or integrate. Sine and cosine, e to the x. So these are the ones, when you have a combination of the sines and cosines or an e to the x, this is going to be the integration by parts of the twist. There is one other example of it that we'll get to in the next section that we'll see. But usually, integration by parts of the twist is this setup, exponential and sine or cosine. And it's not going to matter where you put each function. It's not going to matter. You can do whichever makes you feel happy. If neither makes you feel happy, do both. And confirm that you get the same answer. Okay, so on the left column, we differentiate. We're going to use the chain rule, so we're going to get negative 2 e to the negative 2x times dx. On the right column, integrate. Integral of the sine function is negative cosine function. So negative cosine, same angle, but then we have to do RCR over 3, divide by 3. The derivative of the angle is 3, so we have to divide by it instead of multiplying by it like you would with the chain rule. Okay, now, at this stage, I'm going to jump ahead a little bit. We're going to want to create an equation. Normally with integration, you start with your integral and you're sort of simplifying as you go. You don't think of the equal sign in that process as an equation. You don't do something to both sides. You're just simplifying. You're progressively simplifying your original integral. We need to set up an equation here, so we're going to need to, it's going to be helpful to call this something. Most of the books call it I, capital I. I've gotten into the habit of calling it capital omega. That happened one semester. Someone loved the capital omega and said, can't we use a capital omega? Yeah, sure. Let's use capital omega. It's a cool symbol. So capital omega is the original integral. So the original integral is going to be uv. So uv, so we're going to have minus 1/3 e to the negative 2x cosine of 3x. So there's uv minus the integral of the bottom row. Bottom row is the voodoo. When we multiply that together, we get a positive. So that's not going to change the sign that we already have up there. So we're going to end up with, and I'm going to leave the constants on the inside because of what we talked about earlier. It's always going to be easier if you just leave all the constants on the inside. Cosine 3x. So here is where we are at our crossroads. This is the crossroads where we ask ourselves, is this integral easier or harder than the original? And our conclusion would be it's neither easier nor harder. It's the same. Right? There's a 2/3. That doesn't make it harder. That's just a multiplicative constant. But we have an e and we have a cosine instead of an e and a sine. It's the same. This is fine. With a twist, that's what we want. We don't want it to get harder. With a twist, it can't get easier. So we're going to use integration by parts again. And when we use integration by parts again, let's use our little trick that we just talked about. We've got this leading minus. It's always easier if we have a leading plus. So let's just move the minus to the inside. It's going to make our life a little bit simpler in the long run. So now we're going to go through our process again. We're going to have a u and a dv. And once again, we want to use the same pattern that we used above. So wherever we put the exponential, put it in the same place. Otherwise, you're just going to undo what you already did. You don't want to undo the math that you already did. So if we used an exponential in u up here, then we use an exponential here. So I'm going to treat this as the first function right there, all of that. And then the second function is that. So u will be negative 2/3 e to the negative 2x. And if we differentiate that, we will get 4/3 e to the negative 2x times dx. And for dv, we're going to use the cosine function, cosine of 3x dx. And when we integrate that, we get sine of 3x
Over 3.
over 3. So that's our reverse chain rule. So we get that. So here's where we're at then. So we have that stuff out in front. So that's all going to stay. Right there. And now we're going to do our ultraviolet voodoo again. And when we do it here, UV main diagonal. So that's, I'm seeing negative 4/3. So negative 4/3. No, that's not what I'm seeing. That's not what I'm seeing. I'm seeing negative 2/9. Negative 2/9. E to the negative 2x sine 3x. So there's ultraviolet, UV, minus the integral of voodoo, bottom row, VDU. So that's this. So I see 4/9 e to the minus 2x multiplied by sine 3x. Any issues using that with that second integration by parts? So we are at a second crossroads. We have a new integral. We want to look at it and observe that, whoa, shiver me timbers. It is the same as the original. It's the same as the original. So here is what we are going to do. So we are going to take that original, and we're going to do this. I claim that we could do this. We could write this as minus 4/9 omega. Because we said omega is the original integral. Right, so omega is the integral of e. And that's what we have right here. So we have negative 4/9 times that, e to the negative 2x sine of 3x. I can say it. That's an algebraic equation. We are back to algebra 1. Or something similar. So what are we going to do to solve for omega? Because that's what we're trying to do. We're trying to solve for omega. We're trying to rewrite omega. So we now want to solve that for omega. So what do we do to both sides? Add 4/9 omega. So on the left side, we're going to think of this as 9/9 omega. When we add, we're going to get 13/9 omega. 13/9 omega is going to be equal to all that. There's one nuance here. One nuance. I'm going to put it in a different color. Plus c. So we know that omega is an indefinite integral, so we know that it's creating a family of antiderivatives. So we know there's got to be a plus c in this thing. Well, that plus c is embedded in this integral right here. So as soon as we move it to the other side, we've kind of obscured the plus c, And so we need to make sure that we introduce a plus c. As soon as we move that omega to the other side, we need a plus c here. And then we just have one step to go. Last step. What do we do to both sides? Isolate omega. Divide by 13/9, multiply by 9/13. Yep, whatever floats your boat. So here we go. So 9/13. So we're going to multiply both sides by 9/13. And that will be the antiderivative that you have been looking for like 20 minutes, if you're lucky. And notice that we aren't going to write 9/13 c. We're going to treat the c like a recycle bin. Just going to mash all the constants to a new c.
So could you tell, you can tell just by looking at the thing, because the exponential will never change, and the sign will just flip back and forth, so if you have anything like that, then you're just gonna have to do this.
Yes, exactly. Yeah, so you should be able to tell ahead. I mean, you know, like this right here, if we have an exponential and a sine or a cosine, those are the classic forms that you'll see the twist.
But you have to do it twice before you can do this.
You're going to do, yeah, you have to do it twice before you're going to see the pattern. That's right, before you're going to repeat.
If the coefficient of omega doesn't affect c, can't we just add c at the very end?
You can, but you should, as soon as the omega is all on one side, this right-hand side should have a plus c on it. But yeah, so just make sure you get it in there by the very end, for sure.
What happens when you have a product of more than two functions?
You pair two of them together and keep the other one separate. Could be very complicated. Could be very complicated.
You
Carter?
must have missed this. Why don't you multiply c by 9 and divide by 13?
Because this c is for this line,
Okay.
and if somebody said, hey, omega is equal to blah, 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 and x is equal to blah, 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 solve for c, you would do it right here. These two c's are different, and so if you had to plug stuff in, if you plug stuff into this equation, you'd be solving for that c. If you plugged into this equation, you'd be solving for that c. So even though they are different, we just leave it as c, and we understand that we're never going to go back to a previous c. We're down here at our final answer. We're going to use that c if we had some initial value that we were going to plug in. We just use the last one.
Why is it 2 over 13? Is that just simplified fraction?
So if you multiply by 9 over 13, the 9's cancel. Right, yeah. So simplified fraction. Okay, so you all try one now. Try this e to the I took all the coefficients away, they're all 1. So this is as bare bones as you can get. It's the best way to practice the process where you've got all the coefficients kind of simplified to just 1. So you should be able to just fly right through it. All right, let me know if you're snagged and you need a nudge or a kick.
Best case
Oh, you have? Yeah, so yeah, right. Yeah, so you can use it even for twist. Yep. Yep, that totally works. Right? Oh, here's an integration by parts of the twist up here. Twisty Cal 2 students. Doing integration by parts all over the place. Is that the integral negative from the integral? It's super easy to get the side there, so it's yeah, just something. And then you also want to have your dx over here. The dx will always come along in dv row. And what are you going to choose? Yep. So the dv, good. Yes, yes, yes. Cruise along. Oh, yeah, you're already set for that. This class, so you did do positive stuff, right? Yep. I don't see a C.
Oh.
Plus Charles.
Boom. Bada bing. Boom, boom. Boom, boom.
Flying along, flying along. Close. When you add this to the left-hand side, you're gonna, you see it? All right, I'll start writing mine out to catch up with some of you. All right, so I did the first integral here and ended up with that. Is anyone snagged on that? You got a sign issue?
No, it's negative.
Negative, yep. I meant that sign, not that sign.
Oh, yeah.
SIGN.
Yeah.
The SIGN issue.
Yeah.
So, any questions on that? And again, it doesn't matter. You could have put the e to the x with the dv and the cosine with the u. It doesn't matter. If you're dealing with one of these, if you are not 100% comfortable integrating trig functions, if that tends to be a bugaboo, put e to the x with the dv and the trig function with the u. Because then you can differentiate instead of integrate. That might be easier. Okay. Now, I did not push the minus sign into the integral, so we have to be a little careful. So we have uv, that's going to be minus e to the x cosine x. And then we're subtracting off the integral of v du, but because of that minus, we're going to add the integral of v du. So we get that. Say again? Right here? Or here?
From sine to b.
The derivative, oh. Whoa. Oh, I picked the wrong, oh no, wait, what's going on here? I'm confused. Oh, yeah. Bad integration. Bad integration. What's the integral sign?
If you make the first one positive, and then that would make that, wait.
But the integral of cosine is sine.
No, there.
Yep.
If you make that an addition and then move the sign.
Then,
make it
yeah,
inside.
then that could work out for sure. Yeah, I didn't move the minus sign in, so I just chose, I could have chose the minus to go in, and then it would have worked out fine. So I left the minus outside, so my dv is sine x dx, and the integral of sine should be negative cosine. Thank you. Negative cosine. So let's check over here and make sure that we are on track with our signs, our SIGNs. Okay, so we did UV. So U times V is negative. So look right here. So in there, we're going to have a UV minus integral of V du. So this UV here, right there, that's negative. But because of this minus here, we have to distribute, and it's going to make that a positive. And this is a really good example of why pushing the minus inside makes it easier. Makes it a lot easier. It's very easy to make a sign mistake. Okay, so there's our UV. And then we have minus the integral of V du. But this minus here distributes and makes it plus the integral of V du. And we look down here, the integral of V du is negative. So that means that this is going to stay negative right there. Does that make sense? Okay, so we have e to the x sine of x plus e to the x cosine of x minus omega. Minus smiley face. So we have an omega on the left, a minus omega on the right. We add them together, we get two omegas. And as soon as we add those omegas together, we should be putting, a plus c on the right. Plus c. And our final step, all we have to do, divide by 2. So divide by 2 because we want to get 1 omega in the end. But where's your sign? Let's see, something's wrong there. So we had okay, so you moved this minus inside. So we did that. Okay. And then the integral of that is.
I actually lost like 40 bucks. You lost something 40 bucks? Yes, that's all I had. Oh, okay.
Is that plus? It should be a plus because U times V is positive, so that should be a plus. So that's a plus. UV minus the integral. So this should be that should be a minus though, right there, because that's minus the integral of V du. So that's right. And so then this should be minus something over there, and that should be a plus. There we go. All right. So the last step is just to divide by 2. And there we go. Let's see.
Why does that look like a cursed version of the hyperbolic?
It looks like what to you?
One of the hyperbolics almost.
But the hyperbolics are just the exponential growth and decay mashed together. No sines and cosines. If you were to graph that, it's not going to look any. It's going to look all. It's going to be all wiggly. Wiggly. It's going to be all wiggly. All right, we good. Let's go to trig functions. Trig integrals. Someone was asking about this the other day.
Look at the Garmin. No, but it's good. Went the same. Oh, of course.
That's cooler than a Garmin?
Yes.
Garmins are indestructible.
Mine's actually a Garmin.
Garmins are Samsung killers.
What?
So,
Factual statement.
factual statement. All right, no more watches, no more watches. Let's talk math. So we've got a power of 3. We've got a power of 3 on the sine function. So we need to figure out what to do. We know what to do if it's a power of 2. If it's a power of 2, what's our technique? Power reduction. If it's a power of 2 on sine or cosine, we reduce it. So here we're going to look at more general powers And
Gosh, I asked
what
this
we need to do is decide on whether we have an odd or an even power, and then we do something slightly different in each case. So, when the power is odd, we are going to split off a factor for the differential and convert the leftovers. Okay, so we've got a power of 3. We're going to pull one power off and put it over with the differential. And whatever we've left behind, what I call the leftovers. So we're doing this. We're saying, okay, let's pull one off for the differential. So we're going to make this a power of 2. We're pulling one off. And we're grouping it with the differential. So I'm going to refer to these as leftovers. So those are the leftovers. All right, so odd power, split off a factor for the differential and convert the leftovers. Conversion means use the Pythagorean theorem to go to the, in this case, the co-function. Sine and cosine are co-functions of each other. So what we're going to do now is convert those leftovers. So that's going to be 1 minus cosine squared of x multiplied by sine of x. So that's how we deal with an odd power. We pull one off and convert anything that's left, and now we use u substitution. And what do you think the only choice for u would be?
1 minus cosine squared.
Nope. Because if you did let u be 1 minus cosine squared, then the derivative would be chain rule. You bring down a 2, you subtract 1, then you take the derivative of cosine, you get a messy thing. So you're on the right track, you're looking in the right place, but you should just be cosine. Because our goal is we're targeting this. We're sort of saying to ourselves, pick a u so that its derivative is going to be the piece that we split off and paired with the differential. So if we put a sine over with the differential, the idea is we want to let u be cosine. Because the derivative of cosine is negative sine, but it's going to grab the sine. So if we pull the cosine off, we are targeting u to be, if we pull off a cosine, we would want u to be,
Sine.
yeah, no, yes. If we pulled off a cosine, we want u to be sine so that sine's derivative is cosine. Yes, yes. So let's see what happens. So when we let u be cosine, then its derivative is minus sine. And bingo, the yellow box is right here. So we know that minus du is sine x dx. So that allows us to rewrite this as 1 minus u squared. Right, so we said cosine was u, so 1 minus u squared. Sine of x dx is minus du, so we're going to put a du and let's put the minus out in front. And that's an easy integral. So we just have the power rule. So power rule, we have a minus, put a bracket, integral of that's u, integral of that's u cubed over 3. Then we have to have a plus c. We can put the plus c on the outside. And the only thing left to do is distribute the minus and back substitute. So we're going to have minus cosine of x plus 1/3 cosine cubed of x. Not too bad. Okay. So, let's go back up here and look again. If both powers are even, we go with power reduction identities.
Times each other?
Yep. So if both were, if you had a sine squared and a cosine squared, you'd power reduce both, multiply them together, and then do some more power reduction.
Would it be the same if it was a sine like cube? Or sine not cubes to the fourth?
Times the cosine to the fourth, or?
Well, it'd just be sine to the fourth.
Just sine to the fourth, yes.
Okay.
So if you're going to do sine to the fourth, you're going to take sine squared times sine squared, power reduce them both, multiply it all out, which is messy because you FOIL. Yeah. So now when we look at this one, they're not both even. One of them's odd. If one of them's odd, that's the target. That's the one you want to pull a factor off of and convert the leftovers. So we do have an odd power here. So the sine squared, we're going to just leave that alone. It's an even power. But the cosine, we're going to say, okay, well, that's cosine to the fourth times cosine. So whatever power is odd, that's the one that you're chipping away on. You pull one factor off, group it with the differential. These are now called the leftovers. You left them behind. So we pulled off one, left 4 behind. Now we have to convert them to the cofunction. So how do we convert cosine to the fourth over to sines?
Break it up into cosine squared x.
So cosine squared times cosine squared. So we're going to have 1 minus sine squared, quantity squared. Right? Because cosine squared is 1 minus sine squared. Sine squared plus cosine squared is 1. So cosine squared is 1 minus sine squared. Now we are going to do our u substitution. So we're going to let u be sine, precisely so that its derivative is going to grab the cosine that we split off originally. So that part right there is going to become our du. So we will have. Now you could foil this all out right with the signs in it, but it's easier if you convert to u's first. Then you just have one letter. It's going to be easier if you just sort of wait. So now we're going to have u squared times 1 minus u squared squared du. And now we have to foil.
Or we have a product.
Or, yeah, if you want to be really sadistic, you could try integration by parts on that. Not recommended, but for Austin, might be a good exercise. Ow. Ow. Tell me if it works. Try it with integration by parts. So a lot of these powers of trig functions will end up boiling down after you do your substitution, will end up boiling down to simply a polynomial. And we love integrating polynomials. The power rule is one of the easier ones that we can manage. So we'll end up with a third u cubed minus 2/5 u to the 5th plus 1/7 u to the 7th plus c. And then we just have to do our back substitution and plug in the sine function. And we're good. Or at least I'm good. Hopefully you're good. Hopefully it makes sense. All right, is there any of that you want to ask a question about? Question, Jose?
No.
Wait, question? Question, Harrison?
No.
Caitlin, question? All right. So powers of sine and cosine are the easier pairs of powers that we deal with. Question? Good. The secant and tangent combos are a little more complicated. Question?
What if we have a situation where it's like sine cubed underneath the square root? Like what do we do?
Totally different.
Totally different. Okay.
Yeah. Yeah, if the powers are not even or odd, like if you're under a square root, then you've got to hopefully do substitution of some sort. Yeah. Okay, so powers of secant and tangent. These ones are a little more complicated. And now these we are not going to say cofunction. Like sine and cosine are cofunctions. But in this context, secant and tangent obviously aren't cofunctions. Secant and cosecant, tan and cotan. But when we say convert, we mean not to the cofunction, but to the other one. To the other one. Okay, so power on secant, if it's even, we're going to pull off a secant squared. So if we pull off a secant squared, what do you think we're going to let u equal?
Tangent.
Tangent, because the derivative of tangent is secant squared. So if secant is to an even power, we're going to pull off a secant squared with the hopes of letting u be tangent because the derivative of tan is then secant squared. Whatever we pull off, we want to let u be the other function because that'll match the derivative. Okay, so if secant is to an even power, split off secant squared, and if there are leftovers, convert them. Well, okay, this one we don't even have to pull off anything. We can just sort of think conceptually about grouping secant squared with the differential and let u be tangent. There's no leftovers to turn, so this one is as simple as it gets. So we're going to let u be tangent, and that works out nicely because its derivative is secant squared. So this integral becomes the integral of u squared du. So if we let u be tan, then the tangent part is u squared, and du swallows up secant squared x dx. So this is 1 cubed, 1/3 u cubed, and then all we have to do is back substitute, and there's our antiderivative. Okay, so secant to an even power. That's probably the easier of the two categories here. Now, if tangent is odd, so if, yeah,
Will we do an example of the third one, or will we stay with this one first?
this third one here,
Yeah.
maybe. Yeah, that one will show. Yeah, that one will show up. Yep. So let's look at the second one here. So if tangent is odd, so we did secant even. If tangent is odd, we're going to pull off a sectan. So if tangent is odd, we pull off a sectan. And what would we let u equal then? Secant, because the derivative of secant is sectan. Right? So when secant is to an even power, we pulled off secant squared. We're going to let u be tangent because tangent's derivative is secant squared. When tangent is odd, we pull off a sectan and let u be secant because the derivative of secant is sectan. Okay, so here we have an odd power on tangent. So we're going to pull off a sectan. We don't see a sectan. What do? We're mathematicians. We create them. If you want something, create it. Simple. At least simply said. So if we want to create a secant, well, we just do it. We multiply by 1. All right? So the rule if tangent is odd is you have to pull off a sectan. If there's no secants, create them out of thin air. Okay, so we're going to pull off a sectan. So off with the differential, hanging out with the differential, off in la-la land. There's the differential. We pulled off a sectan, so let's see what's left. We pulled off one tangent, so we're left with tangent squared. And we pulled off that secant in the numerator, so now we have that. Okay. Now we convert the leftovers. So our focus is on tangent. Tangent was to an odd power. We pulled one of the tangents away. We have to convert the leftover tangents. Our goal is to let u be secant because there's the derivative of secant. So those are the bad guys right now. We need to convert them over to secants. So here's where you need to know that identity I talked about last week. Tan squared, if you think about that visual, very, very helpful because you're going to use it a lot. If you have a unit circle and you extend beyond the unit circle and you create this triangle, this side is tangent, this side is 1, and the hypotenuse is secant. That visual allows you to use this Pythagorean theorem really nicely. Tangent squared, secant squared minus 1. So we have secant squared minus 1 in the numerator. We have a secant in the denominator. And then we have this sectan that we pulled off earlier. That's just waiting patiently for our u substitution. And again, what are we going to let u equal? Secant. The whole idea, as soon as we pull off that sectan, we know we need to let u be secant because we need to absorb that sectan. And it gets absorbed by choosing secant because secant's derivative is going to take that all away. It's going to take it away. So we will end up with integral of u squared minus 1 divided by u du. Not too bad. What do we do with that fraction?
Break it apart.
Pull it apart.
So you could do it as long division, but when the denominator is just a single term, you can just distribute it into the numerator. The effect of that is long division. So this will distribute and give us u minus 1 youth. 1 child. 1 youth. Integral of u squared over 2. Integral of 1 over u,
ln absolute value.
ln absolute value of u plus c. And the only thing left is our back substitution step. So we will have 1/2 secant squared minus the natural log of secant plus c. That all make sense? Now this is fine in my book as the answer. Totally fine. Totally fine. If you start looking in my math lab, there are times where you may have a slightly different looking answer because they love log properties. They love log properties. So notice what you could do. You could rewrite secant as 1 over cosine. Actually, we just need the absolute value on the cosine because 1 is positive. That. And then what do you do with the log of a quotient? Subtraction. You could, if you're so inclined, you could say, oh, well, this is the natural log of the numerator minus the natural log of the denominator. Remembering to distribute that minus. And what's the natural log of 1? 0. So that's gone. So that answer is equally as good. I would accept either. Just be aware that when you're looking at my math lab, You may have that, and you may see that, and be like, what's going on? Yeah.
This way also.
Hear me out.
Say that again, where? Yes, we'll do ln. Yes, because sine over cosine. Sine over cosine. Well, we're going to actually do that one in a minute. Yeah, we'll do that one in a minute. Okay, any other steps there you're not sure about or question on? So even secant, pull off a pair, odd tangent, pull off a secant times tangent. And, okay. So here is where you'll go with where yours was. If you write that as sine over cosine, you can put it in log form. Okay, so let's first do these. So even power on secant, odd power on tan, we have processes. We could use either process here, but let's be thoughtful. If we pull off a secant squared, then we only have to convert a secant squared. If we pull off a sectan, because the tan power is odd, we'd have to convert tangent to the 8th. So we'd have to do tan squared to the 4th power. That's a pitta. So we don't want to do that. We want to go with the secants. So we're going to go with secants. So we're going to pull off a pair of secants. So pulling off a pair of secants, we're going to leave the tangents alone. So tangent to the 9th. We're going to split off a pair of secants. We're thinking of this pair of secants as being part of the differential now. So our target is to let u be tangent, because derivative of tangent is secant squared. Well, if we're going to let u be tangent, we need to get rid of those and turn them into tangents. We need to convert these things that we've been calling leftovers. So those things are leftovers. We need to convert them to tangents. So let's convert those to tangents. So we're going to have the integral of tangent to the 9th of theta, and then secant squared, tan squared plus 1, secant's the hypotenuse on that triangle I keep drawing. Secant's there, tangent and 1. So secant squared is tan squared plus 1. So tangent squared theta plus 1. And then secant squared of theta d theta. Now we're ready for our substitution. We're going to let u be tangent. No, we're letting, yeah, u be tangent. So du is secant squared of theta d theta. That's going to give us u to the 9th multiplied by u squared plus 1 times du. Distribute the u to the 9th and rumble on. Pretty easy from here on out. So we'll get u to the 12 over 12, u to the 10 over 10, plus c. Back substitute. So we get a 12th tangent to the 12th theta plus a 10th tangent to the 10th of theta plus c. Whew. Wow. Ready to try one? You look ambitious.
We need to multiply, right?
Multiply what?
Oh, okay.
Which part? Do you see it?
Yeah.
Okay, good. Yeah, we're done there. Any step there? You know, good? Very good. Question, Gage? Question free. All right, let's take a look at this one. You guys can try this one. I'm going to do the first step, though. We're going to rewrite this one as tan cubed divided by secant squared d theta. So we have a rule for even secants and odd tangents. That is not an even secant. When we say the power on secant is even, we mean when it's in the numerator. So this one, you all try this one. This one you're going to use the tangent rule, because tangent is to an odd power. So that secant is not to an even power. That's in the denominator. So you have to use the odd power of tan. So odd power of tan, pull off a secant, convert the leftover tans. Go for it.
Will we have a situation where we have to combine using these rules with tangents and secants?
It's just going to be one.
So like if this was like tangent to the fourth theta over secant squared theta.
Then you're in trouble. If it doesn't, I shouldn't say you're in trouble.
No.
But if it doesn't match either, then you're more in this thing here where you're going to use a Pythagorean substitution.
Okay, and so then if we had a question like that on the test, we'd have to remember the Pythagorean identities in the substitution.
Well, you need to know the Pythagorean identities even for all of these,
Yeah.
because we're always
Using them.
doing a substitution with Pythagorean.
Okay.
Right. We always, whenever we convert the leftovers, we're going to do that.
I just mean, we haven't done a single problem, we just did number 3.
Yeah, not
Okay.
yet.
Not yet.
Not
Okay.
yet. Yeah.
Cool.
We will.
Split off secant tangent. Just multiply by secant.
Yeah, split off sectan. Sectan.
Is this right?
Yeah. Yep, good. Wait, is this? I need to put my glasses on before I say yes. That's odd. So this still is cubed, right?
Oh.
Right, that's still cubed. But yes, we do multiply by that. 100%. 100%.
I tried this first. I can't do that.
Yeah, we wish. Wishful thinking. Wishful thinking. So when tan is odd, you pull off a sectan. There's no secant in the numerator, so what do you have to do? Multiply top and bottom by secant. So yeah, so here you've got your tan cubed. If you want to pull off a secant times tangent, you have a tangent, but you don't have a secant, so you're going to have to multiply the numerator by secant. Anna? Brainwave.
I think you're doing this.
Yeah. You good? Actually, I should take roll real fast. Daniel is here, Ryan is here, Caitlin, Aiden, Maddox, not here. Harrison, Austin, Landon, Quee, Carter, Jose, Arenas, Yanel, Anna, Deepa, Gage, Ari. All right, so.
Yeah, this one does.
All right, so that is our first major spot. The power on tan is odd, so we know we have to pull off a secant. There are no secants. If there's no secant to come along with the tangent that you're pulling off, you create one, and then you offset it by dividing by the same secant so that you end up with a multiplication by 1. So now we have a secant in the numerator. Now we can split off a sectan, pull off a sectan, and we're going to be left with a tan squared. So that's our first major step. Get to that point where we have sectan pulled off. Now these are the leftovers. You're focusing on tangent. Tangent was to an odd power. You pulled off a sectan. These are the leftovers. So those have to be converted. And those are going to be converted over to secants. So tangent is secant squared minus 1 over secant cubed. And now we're ready for u sub. What do you think we're going to let u be? Secant. Yep, because the derivative of secant is secant tangent, and that's what we have off on the side. So we're going to let u be secant. So du will be secant tangent times d theta. So when we jump in here, we're going to end up with integral u squared minus 1 over u cubed du. Question? Yeah.
You don't square the secant squared u minus 1 because it's tangent squared?
Tan squared is secant squared minus 1. Yeah, so the square is just on the secant.
Gotcha.
Yep. Square is on the secant. So what do we do with that fraction now? Carter, what do we do with the fraction?
Let's split it.
Split it. Good. Yeah. We're going to split it. So we're going to end up with 1 over u minus u to the negative 3 du. Yep. Integral of 1 over u? Natural log u. And then we add 1 to the exponent. We get negative 2 divided by that new exponent. We have that.
Should we leave the negative in the denominator or change to a positive term?
We will change, definitely change. So we're going to end up with natural log of secant. Natural log of secant minus or plus 1 over 2u squared. So 2u is secant, so 2 secant squared plus c. A secant in the denominator is what in the numerator? Cosine. You could also do some shenanigans with this absolute value of secant here. That's not so important, but they would definitely be looking for this part to be converted to cosines. If you have a trig function in the denominator that can be simplified by putting something in the numerator, good idea.
Change the exponent. Just kidding.
Huh? Wait, what? You using your eraser creatively? Wait, what? What'd you do?
No,
He's
so
trying to-
opposed to the u method.
I
He's trying to do.
don't know how to do U sub. But I have another method that works about 6% of the time.
Go for
It
it.
got me through calculus.
Can all the trig functions in the denominator be?
Yeah, they could be lifted. That is fact. So one thing we could do is write the secant as 1 over cosine and use a log property if we wanted to. Can anyone see it in their head what that would simplify to if we did use a log property right there?
I do.
And natural log of 1 is, so we'd have minus
Oh, it works, it works.
natural log of cosine.
Listen, I combined it with this.
Oops, that's a theta.
How did you?
I don't know, I somehow did that.
You just did? Okay.
Because secant is 1 over cosine. So log of a fraction is log of the numerator minus log of the denominator. The natural log of 1 is 0.
What's that one meme with the British guy, like, sometimes my genius is frightening.
Sometimes
She's
your
a
genius
car.
is
She's
frightening.
a car. Let me rephrase that. You don't know that, yeah, okay.
All right, so let's not do math for a moment. Let's do cooking. So when you look at these identities here, these are all generated from using a bunch of integration by parts repeatedly, these formulas. Look at them for 5 seconds and let's see if you can memorize them. Psych! No, you don't need to memorize those. If I want you to do cooking on the exam, I will give you this recipe.
Okay.
All right? I will give that to you. You don't need to know those. You don't need to know those. Don't know. Remembering those is ridiculous. That would be crazy.
By extension, you would do the same thing on the final.
100%. 100%. So now let's just make sure you can understand how to use these. So we'll do one example of this non-math math. So when you look at this, is it clear to everybody that the n value is 5 at that moment?
Yeah.
Right, secant to the 5th, so that's n. So if we were going to do this with this cooking recipe here, we would have to say, okay, that's going to be secant cubed of x times tangent because n is 5, and we subtract off 2, and we put a 4 in the denominator, and then we're going to get 3/4 integral of secant cubed. So everybody okay with that? So we're basically just going into this line and replacing all the n's with 5. But now we're also dealing with another power on secant that's odd. And so now what's n? What is n now for this secant cubed? 3. So same idea. We're going to jump over here and replace everything with a 3. So we're going to get secant to the 1 multiplied by tangent. Man, cooking is hard. And then we plug that 3 in there. We get 1 over 2. And then we get integral of secant. So we have that. And our final step will be, so that secant is integrable. I'm going to write down the antiderivative today. We will talk about why it is what it is on Tuesday.
I can't. I'll pull it up to
So you are just going to accept this fact today. But on Tuesday we will talk about why the integral of that is natural log absolute secant plus tangent. So we'll talk about that piece on Tuesday. I will train you on how to do that. So secant is to the 1, that's its antiderivative, natural log of secant plus tangent. All right, let's stop for now. Have a fine weekend. And by fine, I mean do a ton of math. Do some imperial math.
I think I'm going to get your copy of that one.
What a clown. Clown announced.
Because there's the sometimes
You
I
little
use
clown.
spreadsheets, but then there's also
But yeah, you
I'm
so
something else scientist myself.
I made it
Yeah, I've seen it
It works so
intertwined.
easily.
But I made
Yeah,
it
they're
right.
both.
Like of all things.
I had a lot of trouble making it the first time.
Now you've relearned it, it's like
Carter.
I mean, that's how you internalize things, you forget.
I tried learning it the first time, and then I put that in, and I made it my own.
Yeah, and then.
It doesn't work for square roots, but it does work.
Have a good weekend.
I mean, technically.
We worked it out.
Yeah.
We're gonna get through there, getting
I
there.
know,
Arenas?
ChatGPT.
Oh.
Apparently.
Apparently they're like, it's a really good place to get sources.
Every time I've tried using anything AI related, I'm always the worst.
Really? Oh.
It's probably a user problem, but still.
Maybe you're just not asking the right
Just
question.
use photo map.
Photo map? That's
It worked for mine too.
Oh, let me hit pause.
Okay.
Well, I'm
Yeah,
not trying to
so
like
you're gonna
solve it.